Till now, we have discussed in very detail the Dirac equation. We have also seen the concept of Dirac matrices and several illustrative examples we have seen in the previous lecture to clarify our concept regarding the Dirac matrices. Now, actually, we will see the further lectures on this Dirac theory for the success of Dirac equation. In fact, in this success story, our first lecture is regarding the spin of Dirac particle. You know that the concept of a spin has no classical analog. It means there was no idea of a spin of a particle in classical physics. And when in dealing with the atomic spectra and fine structure of hydrogen spectrum, it was seen that the theory which was available at that time was not successful to solve such problems like anomalous Zeeman effect. So to solve those problems, Gordon-Schmidt and Uhlenbeck has proposed a hypothesis regarding the spin of electron. Okay? But that was just a hypothesis, although that hypothesis was verified experimentally by Stern and Gerlach. You have studied in my previous videos on atomic and molecular physics in very detail the famous Stern-Gerlach experiment. But regarding the spin of electron was not any available theoretical aspect, or you can say that theoretically a spin of the electron has been not proved before the Dirac theory. As I have told you that a spin of electron was just a hypothesis, and that hypothesis was experimentally verified, but there was a lackness of an appropriate theory to prove the spin of electron. But when this relativistic equation proposed by Dirac was established, then it was found that this Dirac theory confirms the spin of electron. So basic aim of this lecture is to show how we can say that the Dirac particle or the particle which obeys actually Dirac's equation has a property of a spin. You have seen that the Klein-Gordon equation is applicable for a spinless particle. On the other hand, this Dirac equation is applicable for the particle having the property spin, which is an intrinsic property of the particle. So the basic problem which is in front of ourselves is to show that Dirac particle has a spin. So I have mentioned here what is the problem of this lecture. The problem of this lecture is to show that Dirac particle has a spin. I am not using the word electron, but I am telling you in general that Dirac particle. Okay, so electron is just an example of Dirac particle, but we will see in general any Dirac particle must have a spin. Okay. So how we can say that Dirac particle has a spin? Actually, this argument that Dirac particle has a spin is based on the idea that the rotational symmetry of a free particle system requires that its total angular momentum must be a constant of motion. Okay, you know that in other words you can say that if a particle is moving in a central force field, you know that the angular momentum in that condition remains conserved, and we simply say that the angular momentum is a constant of motion. So when you say that Dirac particle has a spin, this idea is based on the fact that the free particle system requires that its total angular momentum must be a constant of motion. In other words, you can say, if you say that the total angular momentum of the particle is a constant of motion, then in the language of quantum mechanics, you can say that the angular momentum of the particle must commute with the Hamiltonian h. Because you know, any operator which commutes with the Hamiltonian operator, that is a constant of motion. Okay, so if the total angular momentum will commute with Hamiltonian, we will say that the total angular momentum will be a constant of motion. And from this, it was focused that the particle must have a spin. But how? In fact, before the hypothesis of Uhlenbeck and Gordon-Schmidt regarding the spin, it was believed that a particle has only one type of angular momentum, and that is called orbital angular momentum. Okay, but it is found, you will see that the orbital angular momentum operator, this L hat, does not commute with the Hamiltonian operator. L hat does not commute with the Hamiltonian operator. We will see, okay, where L hat is actually the orbital angular momentum operator, and you know this L is defined by this R cross P, okay. But if we define a quantity like S in a proper manner, we will see how it should be defined. And after defining this quantity S hat and adding it in the orbital angular momentum operator, we get a quantity which will be called total angular momentum, represented by the symbol J. Then you will see that this J will commute with H, and this J will be a constant of motion. But for this, how we will define actually this S, how S should be defined, okay. You can see that if S is defined in a proper manner, which we will see in this lecture just now, then the total angular momentum commutes with the Hamiltonian. In fact, this S, which has been added in L, is identified as a spin angular momentum, okay. And so the definition of angular momentum of a Dirac particle or a particle like electron was incomplete if you consider only the orbital angular momentum. It means such particle must have another angular momentum too, which is actually called a spin angular momentum. And when we consider this spin angular momentum and add it in the orbital angular momentum to get the total angular momentum, then it is found that the total angular momentum commutes with Hamiltonian, and that total angular momentum is a constant of motion, okay. But how we can say that the Dirac particle has a spin angular momentum? For this, let us start to see that the origin of this spin angular momentum. And regarding this, let us first of all find the commutator of Lx hat and H hat. Lx hat, this is actually the x component of orbital angular momentum, and we will try to find this commutator. But remember, here the Hamiltonian must be the Dirac Hamiltonian, okay. It is not ordinary Hamiltonian or non-relativistic Hamiltonian, but it will be the Dirac Hamiltonian, okay. So let us try to find the commutator of Lx hat with H hat. As you know that this H hat operator, which is actually the Dirac Hamiltonian, this is defined like this. This is C alpha dot P plus beta mc square, okay. C alpha dot P plus beta mc square. And so this commutator will be equal to commutator of Lx with C times alpha x px plus alpha y py plus alpha z pz plus beta mc square. Okay. In fact, this alpha dot p can be written like this: alpha x px plus alpha y py plus alpha z pz. Okay. Now, using the property of commutator, you know this commutator can be written as commutator of Lx hat with C alpha x px plus commutator of Lx hat and C alpha y py plus commutator of alpha x and Lx and C alpha z pz and plus commutator of Lx hat and beta mc square. Okay. In fact, you can see my previous video, and definitely you have watched the videos on the commutator. There you will find that the commutator of Lx hat with Px hat is simply equal to 0. If you have not watched my video on this commutator, you should watch it, and there you will find this result. Okay. And as the commutator of Lx hat and Px hat is 0, so you can easily say that the commutator of Lx hat and C alpha x Px hat will be also equal to 0. Again, you can try to find the commutator Lx hat and beta, and that will be also equal to 0. I have not actually simplified this commutator, but you know what is the meaning of this beta matrix and this Lx hat, and following the matrices associated with this, you can easily prove it. And so this Lx hat and so the commutator of Lx hat and beta mc square is also equal to 0. Okay. So the first term in the equation number 1 in RHS and the last term both vanish. So the commutator of Lx hat with H hat will be simply equal to these two commutator, which I am just ticking here. Okay. So now we will try to find these two commutators to get the commutator of Lx hat with Dirac Hamiltonian H hat. Okay. So now let us see the commutator of Lx hat and C alpha y py hat. What will be this? This can be written as C alpha y commutator of Lx hat and py hat. Okay. Again, I am suggesting you watch my video on commutator. There you will find the different commutation relations of the orbital angular momentum operators, and there we will find that the commutator of Lx hat and py hat is simply equal to IH bar pz, IH bar pz. So this it will be equal to C alpha y IH bar pz. Okay. Again, the commutator of Lx hat and C alpha z pz hat. This can be written as C alpha z commutator of Lx hat pz. And again, this commutator Lx hat pz hat is equal to minus IH bar py hat. I have not simplified these commutators because already I have dealt with these commutators in my previous videos, so I have written the result directly here. Okay. Now from that equation number 1, you can now see the commutator of Lx hat with the Dirac Hamiltonian H hat will be equal to what? That will be equal to this plus this, and that will be simply IH bar C alpha y pz hat minus alpha z py hat. But you can see this is not equal to 0. And so you can easily say that the x component of orbital angular momentum operator does not commute with the Hamiltonian or Dirac Hamiltonian. Okay. And so Lx hat cannot be a constant of motion. Now, as you know that this commutator Lx hat and h hat is equal to I h bar dLx by dt. Actually, when you study the dynamical equations of motion, there we express the dynamical equation of motion in terms of commutator, and from there you can see my videos on the Schrodinger picture, the Dirac picture, and the Heisenberg picture. There you will find it, and you know that the commutator of Lx hat and h hat, this is equal to I h bar dLx hat by dt. And since this commutator is equal to this much, so you can write I h bar dLx by dt is equal to I h bar c times alpha y pz minus alpha z py, and this is not equal to 0. Okay, and equivalently you can take the minus as a common factor, and this expression can be written as minus I h bar c alpha z py minus alpha y pz, and this is not equal to 0. So from here you can see that as I h bar dLx by dt is not 0, so you can say that dLx by dt is not equal to 0. And since dLx by dt is not equal to 0, so you can say that Lx is not a constant of motion. Okay. In fact, in the similar manner, when you will take the angular momentum, angular momenta y and z component, then in the same line you can prove that the commutator of Ly hat and h hat, Lz hat and h hat are not equal to 0. Okay. So when the Lx, Ly and Lz are not constant of motion, so their vector sum, that is the vector L, will be also not a constant of motion, and we can say that the commutator of orbital angular momentum operator L hat and h will be not equal to 0. Okay, so you can see I have mentioned it here in this base, on this basis, that the commutator of L hat and h is not equal to 0. Okay, now let us add s hat in L to get the total angular momentum j, that is j equal to L plus s. And in fact s has such a value, s is, or in other words you can say s is defined in such a manner that the commutator of this j with h is equal to 0. Okay, then you can say that j is a constant of motion. In fact, when this s is defined like this, this is s hat equal to h bar by 2 times times the matrix sigma 0 0 sigma, where sigma is Pauli spin matrix. When s is defined by this equation number 4, then it is found that L plus s, that is j, is a constant of motion. It means if you define this operator s hat in this manner, then you will see that after adding this s with L, we get j, and that j will actually commute with h. And then you can say that although L is not a constant of motion, but L plus s, which is defined via this equation 4, is a constant of motion. Okay, but how you can say that this s is defined like this? I have mentioned it here directly, but now we will clarify it, we will prove it. Okay, and for explaining this very important fact, let us define a matrix sigma dashed. So, okay, sigma dash, and this sigma dash is defined by this matrix. This is matrix sigma 0 0 sigma, where sigma, as I have told you, this is actually the Pauli spin matrix. And this Pauli spin matrix, you know, has 3 components. sigma x, sigma y, and sigma z. So if you want to define the components of this sigma dashed, then you have simply to put sigma x, sigma y, sigma z at the places of sigma. Okay, so when you will put here sigma x and here also sigma x, then you will get sigma x dashed. So similarly, when you will put at the place of sigma, sigma y, then you will find the value of sigma y prime. Okay, so let us define the components of this sigma dashed. Okay, so sigma dashed x is defined by this matrix. This is sigma x0, 0 sigma x. Sigma y prime is defined by this matrix, sigma y0, 0 sigma y, and sigma z dashed is defined by sigma z0, 0 sigma z. Well, simply sigma x, sigma y, sigma z has been placed at the place of sigma. Okay. Now we will try to find the commutator of the sigma x dashed with the Dirac Hamiltonian h. Let us try to find this commutator. Okay. As you know, this commutator of sigma x dashed with h hat is defined like this. This is I h bar d sigma x dashed by dt. Okay. And what will be this commutator? This will be sigma x dashed with Dirac Hamiltonian h. But you know that Dirac Hamiltonian is defined by this. This is C alpha dot P plus beta MC square. Okay. Now again, this alpha dot P will be equal to alpha x px plus alpha y py plus alpha z pz. So this expression has been rewritten like this. This is commutator of sigma x dashed and with C alpha x px plus alpha y py plus alpha z pz plus beta MC square. Okay. Now using the properties of the commutator, you can write this commutator as the sum of the different commutators which we have written here. This can be written as sigma x dashed commutator of sigma x dashed and C alpha x px plus commutator of sigma x dashed and C alpha y py plus commutator of sigma x dashed and C alpha z pz plus commutator of sigma x dashed and beta MC square. Okay. Now you will again see here that this first term in RHS of equation 5, this commutator will be 0. And this last term, that is commutator of sigma x dashed and beta MC square, this will be also equal to 0. But how you can say that these two will be 0? You can check it. See here. But in examination, there is no need to evaluate these commutators if you can remember that this first and the last commutator will vanish. You can write this result directly. But I have explained it here. You can see the mathematics. In fact, commutator of sigma x dash beta, although we have to evaluate commutator of sigma x dash beta MC square, but MC square is a constant factor. So we simply evaluate the commutator of sigma x dash and beta. From the definition of commutator operator, you can write it. This is sigma x dash times beta minus beta sigma x dash. Now, as you know, from the definition of this sigma x dash, you can see sigma x dash is defined like this. This is the matrix sigma x0, 0 sigma x. So I have written here this matrix. Okay. And in the previous lecture, we have defined the Dirac matrices, and the Dirac matrix beta is equal to the matrix 1, 0, 0, minus 1. Okay. 1, 0, 0, minus 1. So at the place of beta, I have substituted this matrix. Okay. Now again beta is this matrix 1 0 0 minus 1, and again sigma x dash, this is matrix sigma x 0 0 sigma x. Now this is a very simple 2 by 2 matrices, and you know very well to find the product of two matrices. So after multiplying this first two matrix and these two matrix, you will get, I am not telling how we will multiply, but this is a very simple fact, and definitely you have an idea of multiplication of matrices. So this commutator of sigma x dash and beta is equal to commutator of sigma x 0, sorry, not commutator, but matrix sigma x 0 0 minus sigma x. This has been obtained after multiplication of the first two matrices. Okay, and minus this has been obtained after the multiplication of the second two matrices, and this is again matrix sigma x 0 0 minus sigma x. Okay, and you can see, since these two matrices are equal and there is a minus sign between them, so this result will be equal to 0. Now MC square is a constant factor, so as the matrix, as the commutator of sigma x dash and beta is 0, so the commutator of sigma x dash and beta MC square will be also equal to 0. So as I have told you that this last term will vanish, this will be 0, and you can see that I have proved how this is 0. Okay. Now we will try to find the commutator of sigma x dash and the operator alpha x or the matrix alpha x. Okay. You know from the definition, this will be sigma x dash alpha x minus alpha x sigma x dash. Okay. Now we will again write the corresponding matrices here. At the place of sigma x dash, we will write this matrix, that is, this is matrix sigma x 0 0 sigma x, and at the place of alpha x we will put 0 sigma x as sigma x 0. Actually, in the previous lecture when we have studied the Dirac matrices, then we have seen that this Dirac matrix alpha x is defined by the matrix 0 sigma x 0. Okay, we have studied it previously, so I have substituted the corresponding matrix here. And again alpha x, this is matrix 0 sigma x 0 sigma x prime, so this is sigma x 0 0 sigma x. Now let us multiply the first two matrices in RHS. After multiplication, you will get 0 matrix 0 sigma x square 0, and the product of these two matrices is also same. This is also 0 sigma x square 0, and since both of these two matrices are equal, so these will cancel out and our result is 0. Okay. So as the commutator of sigma x dash and alpha x is 0, so you can easily say that the commutator of sigma x dash and C alpha x px is also equal to 0. So you can see the first term in RHS of this equation 5 is also 0. So this commutator of sigma x dash and h hat will be equal to the sum of these two commutators, which have been written in them as a middle term. Okay. So now we will try to evaluate these two commutators. Okay. And for evaluating those two commutators, let us first of all evaluate the commutator of sigma x dash with alpha y. And from the definition of commutator operator, you can write it sigma x dash alpha y minus alpha y sigma x dash. Now we will simply substitute the corresponding matrices. You know sigma x dash is equal to the matrix sigma x 0 0 sigma x alpha y. You have studied it in the previous lecture. This alpha y is a Dirac matrix and it is defined by the matrix 0 sigma y 0. Okay, and alpha y sigma x, this matrix is at the place of alpha y. This matrix, which is I am just underlining, is at the place of sigma x dashed. Okay, now multiply these two matrices. After multiplication, you can see the product of this first two matrix will be equal to the matrix 0 sigma x sigma y sigma x sigma y 0. Okay, and the product of the matrices in the second term, this will be equal to 0 sigma y sigma x sigma y sigma x 0. Okay, now when we have studied the polyspin matrices, there we have discussed in very detail the different properties of polyspin matrices, and you have seen there that this product sigma x sigma y is equal to I sigma z. If you have not watched my video on polyspin matrices in the playlist of quantum mechanics, I will suggest you go through the videos on polyspin matrices or the spin angular momentum in the previous lecture, and there we will find the detailed discussion of such type of results. So I am writing it here directly because I have already discussed these things in very detail in my previous lectures. So you know that sigma x sigma y is equal to I sigma z, and sigma y sigma x, this is equal to minus I sigma z, because these polyspin matrices also anti-commute in pairs. Actually, this sigma x sigma y plus sigma y sigma x is equal to 0 because they anti-commute in pairs. Okay, so you can see at the place of this product sigma x sigma y, I have written here I sigma z. Okay, and here also sigma x sigma y has been replaced by I sigma z, and this sigma y sigma x has been replaced by minus I sigma z, and this sigma y sigma x has been replaced by minus I sigma z. Okay, now you can take this I as a common factor, and so this will be I matrix 0 sigma z sigma z 0. And when in the second matrix we can take minus I as a common factor, so that minus will become now plus, minus minus plus, so this is plus I 0 sigma z sigma z 0. But what is this 0 sigma z 0? You know from the idea of Dirac matrices, this is nothing, this is simply the Dirac matrix alpha z. So this first term is I alpha z and the second term is also I alpha z, and so this commutator, that is commutator of sigma x dashed and alpha y, this is equal to simply 2I alpha z. Okay, 2I alpha z. But in our equation, the term is the commutator of sigma x dashed and C alpha y py, and we have obtained the commutator of sigma x dashed and alpha y. So now we will see what will be this commutator, that is commutator of sigma x and C alpha y py. You can see easily. This is very simple. So you can see. Okay. But first of all, I have written here that in the similar manner, if you will try to find the commutator of sigma x dashed and alpha z, then you will get that this is equal to minus 2I alpha y. You can try it. Okay. So now in our equation, the commutator is of sigma x dash and c alpha by py, and we have obtained the commutator of sigma x dash and alpha y. So this commutator will be simply 2ic alpha z py. Okay, and the commutator of sigma x dash c alpha z pz, this will be equal to minus 2ic alpha y py. Okay. Now we will substitute these values, that is these two commutators and these commutators also, which you have mentioned it here. The values of all these four commutators will be now substituted in this equation number 5. And after substituting these values of commutators, what will be your result? You can easily say. You will then get the commutator of sigma x dash and Hamiltonian h hat. So what will be that? You can now see it. So this will be a commutator of sigma x dash and h hat, which is equal to actually I h bar d sigma x dash by dt. And after adding this, you can see, since the two commutators are 0, so this will be simply the sum of these two commutators. And in this, you can see this 2ic is a common factor. So this is 2ic times alpha z py minus alpha y pz. Okay. Again, the page has been turned, but it will be just okay. Don't worry. My device is hanging. Okay. Now actually we will multiply this equation 6 by 1 by 2 h bar to cast this equation in a proper form. So let us multiply it. So multiplying this by I h bar, okay, I h bar d sigma x dashed by dt by 1 by 2 h bar. Since 1 by 2 h bar is a constant factor, so you can write it inside this operator. So this can be written as I h bar d dt 1 by 2 h bar sigma x dashed. Okay. And in RHS, when you will multiply by this factor 1 by 2 h bar, this 2 will cancel out, and here there will be h bar. So this is I h bar c alpha z py minus alpha y pz. Okay. Now this equation 7 and one of the equation which we have previously obtained earlier, I am just showing that equation to you. This equation, let us see. This equation number 1a. Okay. Here we have defined the commutator of Lx hat with h hat, which is equal to I h bar d Lx by dt, and this was found to be this much. Okay. Now we will add this equation 1a and the last equation which we have obtained just now. So after adding these two equations 1a and 7, what will be your result? You have seen that in the RHS of equation 1a, the term was simply this with minus sign. RHS was this but with minus sign. So after adding the terms in RHS, result will be 0. So this is I h bar d Lx by dt plus I h bar d dt 1 by 2 h bar sigma x dash, and that is equal to 0. Okay. Now you can take this I h bar as a common factor, and in RHS, since there is 0, so that will removed here from here, and we can write this expression as d dt Lx hat plus 1 by 2 h bar sigma x dash equal to 0. And so you can say that this Lx hat plus 1 by 2 h bar sigma x dash is a constant of motion. Okay. So we have proved that Lx hat is not a constant of motion, but Lx hat plus 1 by 2 h bar sigma x dash, this is a constant of motion. Okay. Similarly, you have seen that Ly hat, Lz hat are also not constant of motion, but in the similar manner, when you will make the same calculation for the y and z component, then you will see that Ly hat plus 1 by 2 h bar sigma y hat dashed, that is also a constant of motion, and Lz hat plus 1 by 2 h bar sigma z dashed, that will be also a constant of motion. Okay, so when we will add all these three vectorially, what we will get? We will get that L hat plus 1 by 2 h bar sigma, that will be a constant of motion. Okay, that will be a constant of motion. We have seen that L is not a constant of motion. Okay, but L plus 1 by 2 h bar sigma dashed is a constant of motion. Okay, actually this term 1 by 2 h bar sigma dashed is written by the symbol s hat. Okay, and so s hat is defined like this. This is 1 by 2 h bar sigma dashed, and so this is h bar 2, and you have defined this matrix sigma dashed by the matrix sigma 0 0 sigma. So you can see, if we define this matrix sigma dashed in this manner, then S will be equal to h bar by 2 times matrix sigma 0 0 sigma, and when we will use this form of S and add in the orbital angular momentum L, then the resultant operator is just a constant of motion. Okay, in fact this S is recognized as the spin angular momentum. This is a spin angular momentum operator. Okay, and so the total angular momentum operator will be equal to L plus S hat. Okay, and as you have seen that this sum, that is L plus L plus 1 by 2 h bar sigma h bar 2 sigma dashed, h bar 2 sigma dashed. Okay, this is actually a constant of motion, and instead of this 1 by 2 h bar sigma dashed, we write S. So, and you can write it equal to J. So you can say that this J, which represents the total angular momentum, which is actually the sum of orbital angular momentum and the spin angular momentum, that is a constant of motion, and so its commutator with Hamiltonian vanishes. Okay, now so actually till now we have seen that the orbital angular momentum of a particle is not a constant of motion. It does not commute with Hamiltonian, but when we add a term S in L, then this sum is a constant of motion. Okay, so and this S is recognized as the spin angular momentum, which was hypothetically proposed by Gordon-Smith and Uhlenbeck. Okay, so actually this Dirac theory gives a theoretical foundation of the spin hypothesis of Gordon-Smith and Uhlenbeck. Okay, in fact from this Dirac theory you can see that the electron or the Dirac particle has an intrinsic angular momentum, and this intrinsic angular momentum is called a spin angular momentum. Okay, in fact this is an intrinsic angular momentum. Why? You know that the orbital angular momentum L is a consequence of motion of the particle. It is defined by L equal to r cross p, and p is the linear momentum which is related to the motion of the particle. But this spin angular momentum is not is motion dependent. It is independent of the linear momentum p, and so you can say that there is no connection between motion of the particle and the spin angular momentum or spin of the particle. So a spin is just an intrinsic property like electric charge, like mass. As mass and electric charge are intrinsic property of our particle, just like that this spin is also an intrinsic property and it has no classical analog. Okay. So first of all, we get a strong theoretical foundation of this idea of a spin from Dirac's theory. It was proposed by Uhlenbeck and Gordon-Smith just as an hypothesis, confirmed by experiment in Stern-Gerlach experiment, but there was no theoretical, no theory to prove the existence of a spin of electron or other particles. But after this Dirac theory, it was theoretically proven that the particles have a property like a spin. Okay, so Dirac theory is the first theory to prove the existence of electron, existence of a spin of electron and other particles. Okay. In fact, we have defined this spin operator in this manner: S hat equal to H bar by 2 matrix sigma 0 0 sigma. But we will see later on that when the linear momentum P is much smaller than mc, okay, then this spin angular momentum simply reduces to the Pauli spin operator. Okay, and this will be simply equal to H bar by 2 sigma. But this will happen only when this P is much smaller than mc. It means in case of non-relativistic motion. Okay, and actually this result shows that the Dirac particle is a half spin particle. When you say that this spin angular momentum operator reduces to the Pauli spin operator, and Pauli spin operator is for half spin particle, so we can simply say that this result, when we say that this S hat is equal to this much, but this will happen only when P is much smaller than mc. This result actually shows that the Dirac particle has a spin half. So when an objective question will be asked that the spin of Dirac particle or the spin of particle which obeys Dirac equation is what? Your answer will be 1 by 2. Half is like electron, like proton, like neutron. These are half spin particle, and collectively they are called fermions. Okay, collectively they are called fermions. Now, the basic definition which we have used for the spin angular momentum operator S hat is like this. This is H bar by 2 times matrix sigma 0 0 sigma. Okay. In fact, this definition shows that the operator S follows the same commutation relations as the commutation relations of the angular momentum operator. You know that the commutation relation of angular momentum operator is Jx hat Jy hat, commutator of Jx hat Jy hat. This is equal to IH bar Jz. You have studied these things in my previous videos on angular momentum. In fact, and cyclic, you can say. You can write the other three relations on this basis. In fact, same commutation relations are obeyed by this operator when we define this operator via this equation. And as you know that the spin angular momentum operator has the eigenvalue j square equal to j times j plus 1 times h bar square. So since this spin angular momentum operator also follows the commutation rules of angular momentum operator, so definitely we can guess that the eigenvalues of j square will be in the same form. Instead of j, we will write here the quantum number s, which is called a spin quantum number. So we can say that the eigenvalue of the operator s square is equal to s into s plus 1 into h bar square. In fact, s is here either an integer or a half integer. When you say that s is an integer, it means s equal to 0, 1, 2 and so on. Then the particle has integral spin, and those particles are called bosons. Those particles are called bosons because they obey the Bose-Einstein statistics. But this s at the same time may be half integral, may have half integral value, that is 1 by 2, 3 by 2, 5 by 2. You can also say that this may be odd half integral. So when it is odd half integral or half integer, then the particles will be called fermions. Okay, they are called fermions. So this spin quantum number is either integral or half integral. Okay. In fact, when we take s equal to half, then this definition of s, which is h bar by 2 times matrix sigma 0 0 sigma. You have studied this thing in my previous lecture on the spin operator. If you have not watched, definitely you should go through those videos, and there you will find very important fact which I have just mentioned it here. But the detail of this statement which I am just going to tell you, you can find in my videos on spin angular momentum. In fact, when you will use this form of definition of a spin angular momentum operator, then the eigenvector have 4 component spinor. When you say spinor are simply vectors in a spin space. Vector in a spin space. Actually, this spinor has some peculiar transformation property. Okay, so a spinor is basically vector, but a vector defined in a spin space. Okay, so this form of angular momentum operator suggests that the eigenvector will have 4 component spinor. Okay, and as it has 4 component, so definitely the concrete theory should be in the 4. This actually implies that our space is not 3-dimensional but 4-dimensional. Okay. And in this discussion, we have actually considered that the space is 3-dimensional. So this description of a spin is not very adequate. It is somewhat inadequate. Okay. So this, I think you have understand the idea of how the idea of a spin was confirmed by on the theoretical basis by Dirac theory or Dirac equation or Dirac Hamiltonian. Okay, so this is a very important concept. Watch this video seriously, write down it your notebook and revise it. Then you will see that each and every step will be clear to you. Okay, thank you very much.